Good morning. I'm here to give you the elevator's pitch, the elevator speech for why or how, then why. First how, then why, to introduce this Bucky Fuller philosophy slash mathematics, I'm going to call it, and you want to have it be in your school, or you want your teacher to cover it, or you would like a course in it, or whatever. You're not coming across as super knowing it all. You're coming across as I'm going to tell you enough to get your interest. I'm interested. Why aren't you interested? Let's study this. In other words, you're trying to plant a seed that will grow into a learning experience around this material without yourself saying, oh, I already know it. I'm like already, super informed. You want to bootstrap, right? Like we do with everything in life. It's like with computer languages. It's like, wow, 2 plus 2, hit enter, I get 4. It's like a calculator, but I'm using Python. Can I do more? Can I do graphing calculator stuff in Python? So you're sort of, yes, you can. You're sort of learning a tool, and you can see that it's a tool. So I'm going to just focus to start on just these two pictures. I'm going to haven't officially started the elevator speech. I should have like a stopwatch, right? Elevator speech means you've gotten strategically, you're in the elevator with some super venture capitalist or something, and you have, or a movie guy, and you're an actor or an entrepreneur, and you're trying to get their interest as the elevator goes up, say 10 floors. And today's elevators are pretty fast. You won't have much time. So I guess you could say, to sort of set the stage, you could say um, we use 90-degree angles for everything a lot. Why not 60, and how would that look? What would a 60-degree approach to geometry be? That's the question. And here you've got two lines, you could say. You've got an equilateral triangle, obviously. Now, wait, does this sound like an elevator speech? How do you show pictures in an elevator speech? Maybe this isn't the best analogy. Maybe you get a few minutes, a 5 minute slideshow. You get a 5 minute slideshow to make your pitch. But this is clearly an equilateral triangle, and it's got two vectors or two edges coming down from the top, left side and right side, and we can count how long they are in terms of units. 1, 2, 3, 4, and 1, 2, 3, 4, 5, 6. So 4 times 6 is 24. And David Koski made the actual graphic here, and it's meant to look like you're using V-Zone. Well, it is using V-Zone. It's meant to look like you're using Zome. You know that little toy? I have some here, but I don't want to get off track right now. But anyway, very cool. So how much area is that? Well, it's 24 if we were doing right angles and we were doing 4 by 6 using a right angle, we'd have 24 squares, and that would be obvious. But what's not obvious, what we don't teach, and yeah, it's kind of hard to just see because there's lots of fractional triangles being cut here, but we actually have 24 equilateral triangles. The colored in space, that's 24. So the area is also 24, but it's a different picture. Instead of 4 by 6 being a rectangle with 24 squares in it, we're saying 4 by 6 is this kind of weird looking triangle. It's got a 60-degree apex, and then it's got 4 times 6, and then I call this closing the lid. You just connect the two endpoints, and there's your area. Okay, I never knew that. That's kind of cool. Let's say you're saying to yourself as you watch this presentation, where can we go with this? Does this take us anywhere? Like, I didn't know this, but what's the use of it? And then you could say, well, let's take this by analogy now to volume. Again, we're using virtual V-Zone, or virtual zone, which is called V-Zone in this case, by Scott Vorthman. David Koski's our artist here. And so he's done a tetrahedron, 1, 2, 3, 4, 5 by 5 by 5, right? All three, like if you all the edges are 5, okay? It's a regular tetrahedron. And we're going to do the same thing. We're going to shade in like we did before. We're going to pick an apex. So here we pick an apex at the top, and we go down 4 by 6, and we get 24 triangles. Now we're going to go down. We're going to start at the bottom, actually. The bottom, and we're going to go up. 1, 2, 3, 4, 5 by 2 by 2. So you see the three rays, you can think of them rays or vectors or edges coming out from the apex, which is the bottom here. 2 by 2 by 1, 2, 3, 4, 5. So that's 4 times 5, that's 20. What is the volume of this thing in tetravolumes? And by tetravolumes, I mean just one of these green guys, right? Pick any corner, just one tetrahedron off the corner. That's our unit. Those are our gallons of water, whatever. You pour those tetrahedrons of water into your target shape, you could say. So that makes sense, right? And the answer is it's 2 times 2 times 5, 20. In other words, just multiply like we normally do. Normally we would do all right angles, and we'd say 2 by 2 by 5, and we'd picture like this prism, this brick, this rectilinear thing, this parallelepiped with all angles 90 degrees, right? That's the usual textbook picture for anything like this. And here's just a logical question. What if we stopped using 90 degrees or not stopped forever or any kind of radical break? We're just saying, how about 60 degrees? Could we use that instead? What would it be like? And I think 60 degrees does stand out as another logical beginning for kind of a thinking in a geometry, right? A lot more hexagons, right? Hexagons are the bestagons if you haven't seen that. So okay, so you've got that far. I think we're already on the 10th floor. It was as it's an elevator speech, it's already too long. So I have to say that it's more of a presentation. But then once you've got that, then you've got what's called the concentric hierarchy. Now, where's my best picture of that? Say here, this is that unit tetrahedron I'm talking about, let's say. Then you've got your octahedron, same edge length. That's going to now, because this 1 by 1 by 1, what's the volume? You just multiply. If all the edges are 1, the volume is 1. You can do it with fractions, half by half by half. You get an eighth. So you get this whole consistent volume framework. The octahedron then, next to it, these two together fill space, create something called it's a lattice, a honeycomb lattice. It goes by many names, very important. That octahedron now has a volume of 4. Very simple whole number. And this cube over here, where the face diagonals are the same as your tetrahedron edges in terms of length, that has a volume of 3. Now, are we saying all the volumes now are going to be whole number? No, we're not. This icosahedron with edges the same as that of the tetrahedron, octahedron, or face diagonal of the cube has a volume of about 18.51 ... Irrational numbers are still there. We're not turning our back on math. And it's dual, pentagonal, dodecahedron. We can compute its volume. They're actually nice expressions using the symbol phi, right? Square root of 5 plus 1 over 2. Can be used to describe the volumes of a lot of these other shapes as well. In a nice way. Let's see other pictures of the concentric hierarchy, we call it. You can see what I'm getting at here. You can see what I do right away, and this kind of goes along with the grain of another subculture I'm aware of, the Urbit people, who are developing a new platform, kind of internet within the internet, or kind of a new internet based on a whole other operating system, Arvo, and there's a developer language called Hoon, and it's very alien, and they call it kind of Martian, and they talk about Martian versus Terran. So you've got an incoming call. I'm going to ignore it for now. Martian versus Terran. Terran Earthian, right? So they're using the same kind of lingo as I am, as contrasting two whole different ways of thinking and doing things. So this would be the Earthian or Terran way of doing things. Terra, Earth. You got the 90 degree angle, right? I've got 3 squares of a cube sitting in a bowl of rice. You can see that's the 90 degree angle that we're all used to. And so this spokes coming out from there would be A times B times C, right? But you can also do this with a tetrahedron. So let's see, where do I have my tetrahedron in a bowl of rice? Didn't I do it in a bowl of rice? Tetrahedron in a bowl of rice. I've got my tetrahedron right next to it here, but I don't see it in a bowl of rice. I'm missing a picture of that in a bowl of rice, but here's my tetrahedron on its tip. And I think that's important. You want to show your tetrahedron with the three edges kind of going upward, I think would be a good idea in your presentation, right? And then you're doing A times B times C and closing the lid, right? Closing the lid means you put the lid on it, as in these pictures. And you've got this whole bunch of connections now to sphere packing and, the whole number of volumes I talked about. I'm still looking for in a bowl of rice picture. Here, oh no, that's okay. So here we've got the 90-90-90 in a bowl of rice, and lying down next to it, you see the 60-60-60 degree angle, much narrower. So there's your correlate. And here's the lid that you would close, right? Except if you don't go equal distance in all three directions from the center, then you might not have a regular tetrahedron, so your lid would be a different shape. But I think you get the idea at this point. What I'm suggesting then is that you develop your own graphics. I mean, you can use mine. These are open source. You can come out here, Martian Math. I'll put a link in the description. You can grab some of these pictures. You can start on your own slideshow right now today. But what you're going to be able to do then is be literate when you access the Bucky Fuller stuff. See these two big books here, Synergetics and Synergetics 2. They have a reputation for being hard to read. They're written more in prose than in math. They're not like, that's why he's not considered a mathematician, really, because he writes in a philosophical language, not in a lot of, squiggles, right? It doesn't look like a math book. But there's a lot of math in it, and you won't necessarily be lucid about it or have that deep an understanding if you don't get a running start. And I think a running start is what I just gave you now, where you can see how the Martians do it with their 60-degree angle versus how the Earthlings do it. And you don't need to use that story, Martians versus Earthlings. But it's what the Urbit people use, and I was using it already too, so I think it's going to work for me. I'll end with this picture. The dual pairs. Now, this is kind of abstract, but these are the 5 Platonic solids. And if you know what the concept of a dual is, that's where the faces become points and the points become faces, and the number of edges stays the same. And they rotate at 90 degrees, usually, the edges. You can see it that way, and they bisect each other if you size them correctly. And so the tetrahedron is its own dual, and then the octahedron and the cube are duals of each other. That's the link. Then you can combine duals, right? You can take the tetrahedrons and combine them, have them crisscross, and you get what's called the duotet cube. So the tetrahedron begets the cube and its dual, the octahedron, beget the rhombic dodecahedron. That's what RD stands for, and this has diamond faces. That's what rhombic means, rhombus, diamond dodecahedron, not the pentagonal dodecahedron, which is over here. These are the 5 Platonics again, tetrahedron being self-dual. The icosahedron and pentagonal dodecahedron, they're duals of one another. And they can be combined, right? And once you connect the vertices from what they beget, you get the rhombic tricontahedron, right? So cube plus octahedron equals rhombic dodecahedron. They're duals of each other. Pentagonal dodecahedron plus icosahedron equals rhombic tricontahedron. And these two are duals of each other. So this is how you get going, starting with the Platonics, right? Platonic solids. Good stuff, right? Easy to remember, good mnemonics. And then you've got the whole number of volumes. You've got 4, the rhombic dodecahedron is 6, rhombic tricontahedron, long discussion, 5 or a little more than 5, cube is 3, and so forth. So then you're literate with regard to the major futurist of the 20th century, I would say. And probably the guy with the most upbeat, sort of positive things to say about what our future could be. Like all of our future science fiction, or most of it, tends to be pretty dark, right? Kind of Blade Runner-y, kind of, Will Gibson-y. Bucky science fiction could be a lot more upbeat and therefore more threatening because, utopianism, we like to diss it because, oh, it's totalitarianism in disguise, but what do we have now in our current dystopia? Isn't it bottom up totalitarianism the way Chris Hedges talks about it, right? So this can be verboten, threatening, radical in the sense that it's suggesting a better world, and that's always a threat to the powers that be. All right, we'll talk to you soon. Have a good day.